Maybe we should answer.
Are we online now? I hope so. Hello? Are we online now? Can you hear me? Oh, okay. That's weather. I think it's already online. But how to close the the Facebook notification? I don't want it. From now, it's time now. Okay.
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 Can you actually hear us?
Okay. Can you hear us? If you can, we can start. Can anyone just have a question in the sidebar? Okay. It just seems it works. I see you. Okay. I think we can start now. And Thomas will give the talk this afternoon to our Z project. So I will give the computer to Thomas.
Yeah, thanks, Liang. Good afternoon, everybody. So yeah, I was asked to actually give that webinar. So it's a test for us. Oh, not working.
No, the Ethernet is okay. You can just continue, I think.
Do we continue?
Yeah.
Okay.
And
so I hope the technique will actually work. And yeah, maybe just a short introduction. So I'm Tom Kaempfer, working at OF since about 6 years and heading here the Department of Groundwater Protection and Waste Disposal, where Liang is doing his 3 months internship right now for the ZIP project. So I have a couple points I want to tell you about today. And that's where actually the slides would be good.
Yeah. Okay, then we just screenshot.
Probably present to everyone, huh?
Yeah. Present to everyone, and it's here full screen. Okay.
Okay, so I thought I'll shortly introduce the company I work at and where Liang is doing his internship, and then there will be the more physics or scientific, applied science anyway, topic about disposal of radioactive waste. What is it actually about? Maybe we start seeing some similarities between the geophysics you guys do and what we do here. And in the end, I'm going to illustrate that with a couple very specific project examples where we have worked over the last couple of years for our clients. So OF is a pretty big company with headquarters in Stockholm. We're about 10,000 engineers working in 3 domains: energy domain, infrastructure, industry. Pretty much all around the world. We have also a good 10,000 clients and have already performed like more than 30,000 assignments. So we're headquartered in Scandinavia, Sweden, but besides the Scandinavian home market, there's plenty of offices in Switzerland, in Czech Republic, and in Spain in particular. And then we have some distribution offices and offices to be closer to the client pretty much all around the world. In infrastructure, this is mostly in Scandinavia. Our clients are found in roads and railway constructions, airport building, urban planning and the environment, or real estate. And we do project management, economics, but also feasibility studies and strategic decisions, design of buildings or road constructions, and so on. In the industry and technology, also most of the services are provided out from Scandinavia, and we are present in the automotive market, in IT, but also in the defense industry, particularly in Sweden. We do mechanical design, for example, for Delaval, the milk machines. That's one of the bigger clients, just to name an example. Finally, energy, and nuclear energy is a sub part of this. So is nuclear waste disposal. We cover really all aspects of energy generation. This includes thermal power plants, hydropower, large scale and small scale, nuclear energy, then renewable energy like wind, solar, geothermal, and also energy markets, where the question is, how do we actually design an energy market? What is best there? And also, how do we distribute energy, transmission and distribution? The energy field is very much guided out from Switzerland, with about 200 engineers sitting here in Baden, close to Zurich. This brings us then to the sub-company to the RF group that is actually based in Switzerland. A short word about our history. We're pretty old, like more than 200 years old, always been in Baden, and since 2007 we belong to the OF group. As I said, the energy sector is where we work in. Again, over all the power producing technologies, and we do also provide environmental services related to energy generation or energy handling. Part of this is how to handle waste that comes out of energy production. If we look at the turnover, we see that hydropower is by far the largest part here, and the others are pretty much split equally between thermal energy, nuclear energy, transmission, distribution, renewable energy, and then my department, groundwater protection and waste disposal, where it's particularly the back end of the nuclear fuel cycle. So what's the groundwater protection and waste disposal, and what do we do? We're about 20 geologists, geophysicists, hydrologists, hydrogeologists, mathematicians, and software engineers that work around everything that is related to the underground, meaning groundwater, groundwater flow, geothermal applications, and then everything that's related to contaminant transport in the underground, and there in particular what's happening to radionuclides that escape deep geological repositories for radioactive waste. This pretty much summarizes what I just said. To do so, particularly with respect to nuclear waste, we have three main areas where we work in. First of all, we need to characterize the underground. So we do have a group working on hydrogeological exploration and characterization, so that we know what is the material we work in or with. Then we do have a other group that has is pretty strong in numerical modeling of processes in the rock in the underground. And we use both of that as a feed-in to the third group that actually works on safety analysis and risk assessment for geological waste disposals. Maybe this was a little abstract about the company, but you might see clearly what we exactly do when we start looking at one specific problem, which is actually radioactive waste disposal. And to make it more easy for me and for you, I picked often an example, as an example, Switzerland. And we probably should just start looking at what is the radioactive waste, how much is there, where does it come from, and what do we have to do with it. So pretty much every country that does have nuclear power production well, every country that has nuclear power production will eventually have so-called highly active waste that comes out of the burnt fuel. This is very often also most of the waste that is in a country at all. There is other waste sources that come from medicine, research, or industrial applications. As an example, in Switzerland, we have 5 nuclear power reactors that are supposed to operate roughly 50 years in total. And the amount of waste we get from that corresponds in volume to about 7 single-family homes, so like roughly 7,000 cubic meters. This is the highly active waste, so burnt fuel pretty much, and reprocessed or waste coming from reprocessing of burnt fuel. Then there's, on the other hand, low and intermediate level active waste. So this is not radiating as strongly or as long as highly active waste. It's considerably more volume, and a significant part of that volume of that not so active waste comes also from medicine, industry, and research. Now, what does that mean globally? I think we can say radioactive waste is, if we just look at the volume or even the mass of it, it's not particularly large. So we have a relatively small volume of waste, but it is rather dangerous for the environment and human life, particularly because it radiates due to radioactive decay for many thousand years. So because some of the radionuclides have very long half-lives, as for instance iodine with a half-life in the order of 1 million years. So what do we do with that waste? So we have not a big volume, but a pretty dangerous waste if it's not handled appropriately. There has been several disposal concepts that have been discussed or come up over the time. There's obviously the possibility one could try to dissolute the waste, so see that the concentration is rather low, and then disperse it into the environment, for example, into the ocean, a practice that has been done until not so long, at least for low and intermediate level waste. There has been the idea to send it to space, with currently, I think it's 5 to 10% of all the spacecraft that actually do not make it off the Earth. It seems like a rather dangerous option. There's transmutation, where there's a lot of research going on, meaning trying to take the waste and through physical processes turn it into less active materials. Works so far at the lab scale. The problem, at least at the industrial scale, is that it consumes far too much energy. So we're not there yet that we can actually treat the waste so it becomes less dangerous. Finally, compared to dissolute and disperse, there's also the possibility to concentrate and enclose. So keep the waste together and see that it is enclosed, put off the reach of humans and away from the environment long enough so that it's not dangerous. There's different solutions. There's the option of long-term temporary storage, for instance, just have a building and the waste in there and see that it's integrated there and not touched for many thousand years. There has been the idea of disposing it underneath the seafloor, probably feasible, but technically very, very challenging. And finally, there's a slightly easier option, is actually to not look underneath the sea, but on mainland, if there's geological layers where we can put in the waste, and then because of the properties of the geological layers, ensure that they are encapsulated and kept off the biosphere for the relevant timescale. It's that last option of the geological disposal that has come out as the international consensus over the last a couple of years, or maybe already 10 years ago. So pretty much every country that has radioactive waste thinks about the concept of deep geological disposal. So the idea is to select a suitable host rock. It has to be geologically stable over a long time scale. Then it has to keep the waste isolated from the biosphere, particularly waste or radionuclides can travel across water in pore space. So if the rock is lowly permeable, this will help. And currently, at least in Europe, there's, and probably even worldwide, one can say there's pretty much 3 types of rock that are considered. There's rock salt, there's clayey rocks, and there's granite rocks that are potentially suitable to dispose waste of. We still have to build a mine into the underground before we can emplace the waste. And this mine, the tunnels and access drifts will have to be backfilled and sealed off properly so that we do not have preferential flow and transport path. So in the end, the safety of such a system is given by a combination of the geological barriers, so the host rock in particular, and engineered barriers like backfilling, plugs, even waste containers. Let's now turn more to the physics. What is actually happening if we emplace waste in a rock layer below the surface? First of all, maybe to give you an idea, what's the dimensions of these systems we look at? I mean, we usually emplace or plan to emplace the waste at several hundred meters deep. In Switzerland and France, very specifically, we think about 400 meters below ground. Now, given the amount of waste, the footprint of the mine where we can put the waste is in the order of square kilometers still, so it's still pretty large. And I already told you, half-lives of some radionuclides are pretty long, so we need to make sure that no radionuclides or no significant amount can escape for time during a timescale of up to 1 million years, roughly. We usually try to select low permeable, small porosity rock. There is one question that comes up if you think of granite, which is very low permeable, as low as it's not fractured. So that's the advantage of clay compared to granite. It doesn't easily fracture, or if it fractures, it might actually self-heal after the fracture. So imagine a low permeable rock. We build a mine into it. This mine does have a mechanical impact. There's an engineered damage zone, which increases porosity, increases permeability. This is a concern one has to take care of. Mining will also lead to desaturation, so there is potentially multi-phase phenomena underground. We then emplace the waste, backfill the tunnels, leave the system for itself. The waste will, however, due to radioactive decay, produce heat. So we do have significant heat production. This heat has to dissipate away. We might also have metals, for example, down there that may corrode. If there's corrosion, this may lead to gas production. If there's anaerobic corrosion, in particularly hydrogen will be generated. Nevertheless, also there's maybe a gas phase. Eventually the system will resaturate. Water will get into contact with radionuclides. Radionuclides do dissolve and are transported away. Now the goal is just to create a system that this happens only after many thousand years and radionuclides are not radiotoxic anymore. That was the overview of the phenomenology. Let's now look at processes. If we try to model and predict the behavior of such a geological system over many years, what's the transport and flow and physical processes we have to look at? There's definitely flow and transport through a rock or different rocks that can be considered porous media, maybe porous and fractured media, depending on the rock. There is a multi-phase flow happening. We do have liquid and gas phase. Driving forces for the flow through the pore space are, on the other hand, obviously pressure gradients that might come just from hydrostatic pressure differences, but it might also come from induced pressure differences, for example, due to thermal heating that leads to pore water expansion, pressure increase, and thus water flow. Density gradients is an issue too, or a driving force for flow processes. Not surprisingly, flow velocities depend on the permeability of the rock, on the fluid viscosity, thus on the fluid composition, and on the interaction of phases if there is a gas and liquid phase present. Now, often the phases are actually not single component, but multi-component phases. We can have water in there, we can have hydrogen, we can have radionuclides, we might have salt, and so on. In the end, flow and transport is advective, dispersion is playing a role, and there's a diffusive component. We might further have retardation processes that will lead to slower transport of, for instance, radionuclides. This can be sorption to the solid in the rock, or also precipitation dissolution phenomena if there's solubility limits. Finally, if we're interested in radionuclide transport, radionuclides will decay into other elements. So decay chains might have to be considered. Besides the usual or general flow and transport processes, there is heat generation and energy dissipation processes that have to be considered, particularly for highly active waste that produces considerable amount of decay heat. For a typical waste container from Swiss nuclear reactors, even after 40 years of temporary storage at the surface, there's still temperatures at the waste container surface that can go far beyond 100 centigrade. This energy must be dissipated through convection, conduction, radiation, through the rock. There is criteria that we have to take care about. If certain rocks, particularly clay, get hotter than roughly 100 centigrades, they may lose some of their isolating properties for radionuclides. So we may have to make sure that we emplace the waste in such a way that temperatures do not go above a certain threshold. I already said that earlier, temperature increase may lead to expansion of liquid and solid phases. This impacts stress states. And in the end, this one of the consequences here that we will actually have to look, if we think about modeling such a system, to model energy, hydraulics, and mechanics in a coupled way. Another relevant process is gas generation. On the one hand, due to anaerobic corrosion of metals that releases hydrogen. On the other hand, some wastes do also contain organic substances, and very likely there's microbes close to the waste that might lead to decomposition and methane release. As for the temperature, if there's gas released, this may lead to pressure increases. It might even lead to the formation of a gas phase if the gas cannot dissolve quickly enough into the liquid phase and diffuse away. So it might, even after having closed off the repository, lead to maintaining multi-phase conditions over a couple hundred or thousand years. Finally, we also have to consider mechanics, in particular geomechanics. The formation of the engineered damage zone is definitely a concern. It might lead to preferential flow and transport paths along tunnels, drifts, and shafts. There also, because of the energy and gas release and the increasing pressures and stresses, rocks might fracture. And there, it's important to see what kind of rock we're in. Is fracturing critical, or is it maybe not so critical? For example, clay rocks with very low permeability, they might fracture if the pressure is high enough, but very likely once the pressure has decreased again, it's a self-sealing property of clay rock, so fractures will close again, and the rock will again become low permeability. Salt rock does also have interesting properties. Salt creeps, and so in the end, if you dig a mine into a salt rock, and if there's overlaying pressure, that mine will close off by itself, just by the creep of salt. Salt has some disadvantages. It's soluble, so water intrusion must be avoided. Granite, on the other hand, does also have advantages and disadvantages. There's no big issue with heat in granite, for example. However, as soon as there's fractures, these fractures are preferential flow path, and so the waste must be sealed off additionally. I don't know, I probably shall just go through the presentation and then there's questions at the end. Mm-hmm. Okay, I thought just to close off that webinar with a couple of projects, specific work that we do for our clients related to radioactive waste, and even a little beyond, to show you where also we apply our knowledge. But let's start first with radioactive waste. I told you we do have a group that is concerned with assessing the properties of potential host rocks, and particularly clay. And there we do, for more than 10 years now, we support ANDRA, which is the French agency taking care of the radioactive waste in France, in their studies in a rock laboratory in Bure, which is an hour or so northwest from Nancy towards Paris, close to the site where ANDRA plans to build its deep geological repository. There is a rock lab at about 450 meters depth within the potential layer where the waste galleries shall go. This is the so-called Callovo-Oxfordian clay. There's plenty of observations and long-term experiments going on that have the goal of determining, for example, permeabilities, but also transport properties, how the rock reacts to overpressures, to temperature increases, and so on. So we do all the data analysis with respect to hydrogeological characterization, compile these into synthesis, help the client also present the results to authorities. Not only deep underground, but also close to the surface, there is hydrogeological characterizations going on. particularly close to Buer. This is because we have to build access tunnels to the future repository, so one needs also to know how the geology behaves close to the surface. Another point, and that's the project example here, is Andra in France also does have storage facilities for low-level radioactive waste planned that will be much closer to the surface, and so they are interested in knowing the flow and transport properties of rock layers just like 50 to 100 meters deep on the ground. Let's now leave the observational and characterization part and jump to numerical and physical analysis of the geological repository systems. Again, in France, in a clay formation, we have built a full 3D model of an emplacement tunnel. And actually, we have expanded this model to a full-scale repository model with a couple hundred emplacement drifts, where the model allows us to simulate coupled gas and radionuclide and heat generation and dissipation. We have programmed that simulation using a code called TUF2, and particularly for the full-scale simulations, we are forced to use the parallel version. So we do have actually a fully parallelized model to simulate a repository system at the scale of a couple cubic kilometers. We use that model on the one hand for phenomenological studies, but also for sensitivity analysis, and this on a time scale of really up to 1 million years, which is usually what the authorities ask for. Now, doing these models, we've realized that some codes that are available, as for example, TUF2, does not have all the phenomenology or all the physics implemented. So that's why we have a couple people that are familiar with programming and implementing physics into code. So as an example, what we have done, we have taken that TUF2 code and implemented, on the one hand, arbitrarily long radionuclide decay chains, and on the other hand, precipitation dissolution phenomena. So in order to simulate precipitation of certain radionuclides. When we do such developments, it's always important to test your code and implementation, to do benchmarkings, and then do a proper code release that goes together with documentation of the code development, and obviously also a user manual. Let's now leave France and look at Switzerland. In Switzerland, we also, for the NAGRA, which is the Swiss National Agency for Radioactive Waste Disposal, safety calculations, where we simulate radionuclide release and transport from the waste containers all the way to the biosphere. What's maybe new in Switzerland, what we've done also, is probabilistic safety analysis with many thousands of simulation runs that allow us, on the one hand, to determine which are the most relevant parameters that do actually govern the system comportment, and on the other hand, also give us an idea about the safety in case of not so well-known parameters. These simulations are then the basis for so-called safety analysis, so where the goal is to quantitatively show that a repository is safe over a million years. And what you see here in the image to the right is typically a result of so-called numerical safety analysis simulation. And it gives you curves that determine a radioactive dose associated with certain radionuclides for a typical human living close to a repository, at the surface. So the additional doses he will take up because there is a deep geological repository underneath his feet. Now this dose is not supposed to exceed a certain threshold that is given by law. So these simulations particularly help to support the applicant, which in Switzerland is the NAGRA, through the licensing process. That was pretty much all with respect to radioactive waste. I have 2 or 3 more slides showing you that there is parallelisms between the physics of radioactive waste disposal and other geological and hydrogeological questions that are asked and projects. So, for example, OF Consult Switzerland is constructing the enhancement of a pumped storage power station in the Valais, the Nord de Drance project. For people that know Switzerland, it's just above Martigny at the Lac Émosson. And my department provides hydrogeological consulting during the gallery construction. And now, once the galleries have been constructed, there's a long-term hydrogeological monitoring that helps to avoid drainage of the dams. So since we model flow and transport processes in the underground, there's no need to do that only for very low permeable media and radioactive waste, but we can do also similar studies for big aquifer valleys in Switzerland. So we do have several, for example, in the Reuss Valley close to Lucerne, we do have models of groundwater flow that we can use then to study interactions of infrastructure with groundwater that we can use for thermal applications, heat pumps, placement of heat pumps, heat storage maybe even in the underground, and so on. Finally, geothermal applications also to create power do need our expertise. As an example that we have done recently, in Jordan, in the Middle East, we have studied in the area of a potash company if it would be feasible to produce power from geothermal sources. I think that was it for that webinar and the overview. And yeah, obviously, if you have questions, you have probably typed them. And
okay, yeah, we can see the questions now. Okay, first, thank you, Thomas. Give us a very interesting talk, and we know something about the applications in industry, which in this area we are not so familiar with, because our deep project is a science oriented project. But I think our fellows are also very interested in maybe they want to know how to make the applications with our knowledge to in the industrial field. Mm-hmm. Okay, so let's have a look at the questions.
Yeah, maybe we have to move that a little bit.
Yeah, maybe the first one. Leah.
To have all.
See that. Okay.
Okay, there was a question. If all the countries have the same thresholds concerning radioactive waste, I guess if I understand the question well, it is about thresholds for the additional radioactive dose that people will take up. There is not in all the countries the same thresholds. They are, I do know the situation in Switzerland and Germany pretty well, and there it is the same values. I think in France it is slightly different. So the answer is no. Just legally, no.
Okay.
Yeah.
Okay, we cannot know what's their response because we cannot hear them, but I think we can continue.
Yeah.
Yeah, that's done.
Okay.
This one.
How safe is the storage in a salt layer? Isn't there a risk of dissolution when fluids intrude? Exactly. I mean, there is a. I think I mentioned it in a repository in salt. Water intrusion can become an issue. As an example, there is a salt mine in Germany, the Asse salt mine, that has been used as a research. Well, it has been a mine to extract salt, and probably like 30 or 40 years ago, no salt was extracted anymore, and so the mine has been used as a research mine to study storage of radioactive waste. Now, what's happening there? There is actually water intrusion, and this is a big concern because that water does enter into contact with the radioactive waste, and because the salt is still creeping and compressed, that contaminated water, it's kind of a water-salt mixture, will be pressed out of the salt and might actually leak into groundwater. So if one thinks of a repository in salt, it is critical to select a salt dome that is not into contact with water, which is easier if one actually specifically designs a repository compared to the difficult site Asse, where one has used a mine that was not designed to keep water out. It was designed to extract as much salt as possible over a short time period. Okay.
Continue. Okay, Kaempfer.
Question from Kaempfer. Have the maximum dosages evolved over time? Can you expect different legal doses in the future? It might be. It might be that there will be different legal doses in the future. It is a debate quite regularly, also for people that work with radioactive substances. How much additional doses can they tolerate without it being harmful? I'm not so sure that it is highly relevant in the end for the concept of deep geological disposal, because I mean, already currently the maximum doses allowed for by law are a fraction of the natural dose just occurring outside. So at some point it's probably statistically not relevant anymore.
Oh, this is from Sarah, typed this text, but I think it's from Jonas.
Okay. So how safe is salt with respect to its mobility regarding a storage time of more than 1 million years?
That's what we wanted to do.
I'm not sure what exactly is meant by the question. There is there is two kinds of salt rock that are considered, to my knowledge, and one is so-called salt domes, as for example in Germany, and this is salt domes. I don't know how old they are. They're pretty old, and they reside stably there for for many million years already. And so it's very reasonable to expect them to stay as the whole salt dome is for another 1 or 2 years. Now, the mobility of the salt, if you think about if one digs a tunnel into salt, this tunnel will close off. But this is actually an advantage, because once the tunnel is closed off, there is no preferential flow path anymore. So the mobility of salt due to creep is actually an advantage. But it doesn't. I mean it doesn't mean that the whole salt formation will move through the geology. And I mean the second kind of salt areas that are used for disposal, for example, in the US, is layered salt. So it's a big horizontal salt layer, if I'm correct, and this shouldn't be an issue neither.
Okay, let's continue.
Yeah.
This is a question from Italy. Matteo asks,
do you use fluid inclusions to measure permeability in time?
Do you do the measurement?
Now, I do not understand the question as is. The measurements that are usually done to measure permeability is pretty much classical hydro tests. So there's a borehole drilled into the rock. Well, I'm talking about at least the clay rock and the experiments done in France, in Bure. So we drill a borehole into the clay rock, seal it off with a packer, inject water or gas, depending on if you're interested in the permeability of water and gas, and measure the response of pressure, either in the hole where we inject or in a second borehole that has is a certain distance away. And just from this response, we can conclude back on the permeability and storage coefficients, and so on. And these experiments in Bure, they have been repeated now for at least 10 years in order to study and to see if there's an evolution over time. Also, if there is an impact of other building activities around these boreholes. Yeah, that's about what I can say.
Okay,
for that.
Because we are in different fields, and maybe in industry we measure the permeability in different ways.
Mm-hmm. Mm-hmm.
Okay, so let's continue. And Jonas again.
How strong is our consultant involved in public relations work?
Because he's a Swiss.
Aha, okay. We're not very much involved in the public relations work, particularly not in Switzerland, because we do a lot of work for NAGRA, for the National Agency for Radioactive Waste Disposal, and NAGRA explicitly wants to keep the public relations work in-house. So they do not want us that are contractors to them to publicly present our what we've done for them. Now what we do present some of the work we do at international conferences. We also sometimes present projects and some results in in our company brochures, but we do not actively participate for public relations work, at least not in Switzerland.
Okay, we still have time and we can continue.
Yeah, regarding salt storage, what problems occur when drilling into salt horizons? Other evaporities that can become problematic to drill, and volume changes may occur due to fluid intrusion. Now this is the fourth question on salt, and you might realize that I have mostly worked with clay rocks. I must answer a little bit around the question probably. I haven't really heard of technical problems anyway, mining into salt or drilling into salt. It seems to be rather straightforward. And if one thinks the solution of deep geological repositories in salt to the end and says, well, finally the inclusion or the isolation of the waste from the biosphere is mainly provided by the salt, it's not an issue, because you mine or drill, you emplace the waste, and eventually all the openings will close, and so you do have a non-damaged salt rock around your waste. And so as long as you have that, also fluid intrusion is not an issue anymore.
Okay. I think due to the time limitation, we can have the last question. But
we still
sure. Have a lot.
Sure.
You can choose one.
Oh yeah, there's a lot.
Yeah. Maybe we can choose someone.
Oh, no, look, there's just two left. The others is technical for the. So we can do the last two ones.
The last two ones.
No, this is just a
lot.
Like go up.
Go up. Okay.
To the very top. I think there's two. There's just two, or well, there's three.
But it's the same.
Is it dangerous? The application for geothermal energy. Well, I don't know if this question is hinting about seismic events due to stimulation of rocks when one tries to exploit like the enhanced geothermal systems, if one wants to fracture or open fractures in a rock. I mean, my short answer there is there's probably no energy generation option that is free of any danger, and the question is, are we ready to live with a certain risk that there will be seismic activities when we do geothermals? And yeah, it's more a philosophical question. I don't think that there is a significant danger in exploiting geothermal energy.
Okay, so it's finished.
Okay.
Okay, and
thank you very much for your interest. And I mean, if there's any more specific questions, you feel free to send me an email.
Yeah, I will.
Or to Young.
Yeah, I will forward to you.
Okay.
Okay, and thank you everyone, and thank you Thomas, and hope we can meet together again. Bye-bye.
Bye.